Hello everyone, I'm Pickup Lee, the Chief Architecture of Virtual Technology. I'm currently responsible for the department of MariaDB kernel. Virtual Technology is a database ecological product company focused on the field of private cloud, providing enterprise users with high performance, high availability, and scalable open database cloud platform solutions. We encounter some replication delay issue when help our customer to solve database problem. I believe this experience will be useful to people like you who are using MariaDB in product environment. So let's begin the discussion on this topic. You can see the replication structure of MariaDB on the right of the slide. MariaDB write event to binary log when user commit a query on must. Slave use else read to read the bin log from must and write to the local relay log. The circus read on the slave gets the event from the relay log to replay queries from must, ensuring that the queries on the slave is the same with the queries issued on the must. On the slave, you can check the replication delay through show slave status, which you can see on the left of the slide. The value of second behind must represents the delay of replication. As you can see, the second behind must here is very large, which is 1,800 seconds. Let's look at the scenario on the slide. It's a read-write separate infrastructure. Application write on the must and read from the slave. If the replication delay second is 1,800, the data read by application from the slave will be half an hour ago. It's unacceptable. And this is another scenario for database administrator. Application read and write and must. But the slave lag behind the must for 1,800 seconds. If the must get done at this time, the application must be fed over to read and write data on slave, which means over 1,800 second data lose totally. So it is very important to avoid replication delay and ensuring that the data of slave and must are consistent. To solve the problem of replication delay, we need to know the method how to get replication delay. Let's take second behind must for example. Second behind must equals to clock of slave minus last timestamp executed by circus read minus clock diff read must. Clock of slave is current timestamp of slave. Use time 0 of C language to get it. Last timestamp executed by circus read is timestamp of last event executed by circus read. The clock diff read must is the difference between current timestamp on the slave and the timestamp of select now on the must. It is calculated only once when else read is started. As you can see, second behind must is not reliable. For example, if the system time change on the slave, the second behind must is not exactly replication delay because the clock diff must does not recalculate before else read be started. And if the else read and or circus read is corrupted, you cannot get the value because the second behind must is set to null. Someone has listed the drawback when using second behind must to monitor my circle replication delay using Prometheus. Please take a look at the snap. Of course, second behind must is not the only one method to get a replication delay between must and the slave. We can also use PT heartbeat to get the replication delay. It updates a record in the must every 3 seconds, and then get the delay as null minus timestamp of the record on the slave. You can update heartbeat table on the must and use monitor and check to get the delay of the slave on the slave. This is a general method which is more scalable for getting delay of replication. PT heartbeat support post-grid circle and even work when L3 or circle 3 is corrupted. So as you can see, if we want to solve the problem of replication delay, we must let the circle 3 always catch up with the must. So how to avoid replication delay? Firstly, we should care about the server config of the slave. The configuration of the slave should be similar to that of the master, especially the memory and the disk. For example, the master is SSD, solid state driver on an exclusive database server. The slave is HDD, hard disk driver on a virtual machine. You can see the difference of LPS on HDD and SSD on the upper right column. The slave should be much slower than the must. You certainly cannot expect the slave to catch up with the must. If the memory of the slave is much slower than the must, the buffer pool of InnoDB may not enough to hold the cache data, which will also increase the replication delay. Parameters set to MariaDB may also increase the replication delay. Let's look at this parameter in the slide. If the parameter of sync must info, sync relay log info, and sync relay log are set to 1, every time the I/O thread pull a event from the must, it need to sync the relay log and the must info file. Every time the circle thread execute a circle statement on the slave, it should also need to sync the relay log info. It requires more I/O resource on the slave and will increase replication delay. So if the disk has a catch back by battery, consider setting sync must info at 10,000, sync relay log info at 10,000, sync relay log at 10,000, and set relay log recovery as on. Let's look at parallelized replication. Before 5.5, MariaDB only have one circle thread on the slave to apply circle statement. That means that the transaction execute one by one on the slave. If there are more queries issued to the must, the slave will fall behind. The replication delay increased. To solve the problem, we have no choice but only help our customer to upgrade MariaDB to the version of 10.0 or even higher. In the version of 10.0.5, MariaDB provides an awesome algorithm to increase replication performance. It applies multi-transaction in parallel using a pool of separate replication work threads. And must, if two transactions commit together in a group, they are written into the binlog with the same commit ID. Such events are certain to not conflict with each other, and they can be scheduled by the parallel replication to run in different work threads. Database administrator can set the number of slave parallel threads to identify how many concurrent work threads to apply the binlog event upload from the must. And slave parallel thread is a dynamic variable that can be changed without restart MySQL D. In addition, begin with 10.1.3, MariaDB added a consequence mode of slave parallel mode called auto-incrementing, which provides a lot of opportunity for parallel apply on the slave. But it still preserves exact transaction orders from the point of view of application. And now it is the default model from MariaDB 10.5.1. As an optimistic algorithm, it applies transactions in parallel as many as possible. If two transactions try to modify the same law, any such conflict is detected, and the late of two transactions is rolled back, allowing the former to proceed. The late transaction is then retried once the former has completed. The term optimistic is used for this model because the server optimistically assumes that the few conflicts will occur. So there are rarely few actual work spent on rolling back and retrying complex transactions. But the gain from running most transactions in parallel is great. By the way, you should pay attention to MySQL in replication. MySQL does not support transaction. It just provides table-level locking, so you may get large replication delay when using MySQL table, even using the version higher than 10.0. Parallel replication of MariaDB cannot completely solve the problem of replication delay. Let's take a look at this scenario. A transaction in the transaction group submits a long query to the master, such as delete 100,000 records from the table of order. This transaction executes more than 3 minutes on the master, and will last for more than 3 minutes on the slave. Other transactions will behind the group of transactions cannot start to execute before this transaction finishes. The long-run query increases replication delay, but there are many solutions for it. We can change the application to delete only 1,000 rows in a transaction and loop for 100 times. This solution will reduce the log time on the master. Developer would love to change the application. But for DDL, it's not so simple. Suppose the scenario there is an update to item and user info commit in the master, and at the same time another DDL transaction on the table or committed. Here is the circle. All table orders change column order number begins unsigned not known auto-incremental. It will change the order number from int to big int. Same as the delete long query, it will increase the replication delay. The current MariaDB solution can only assume that the DDL will not conflict with other concurrency parallel DML. So you can set GTID domain ID at the session level to allow DML and DDL to execute in parallel, like this. And a more general solution should be GHOST. It creates a ghost table like your original table, alter the ghost table as you desired. Incremental copy data from the original table to the ghost table. Any insert, delete, update applied to the original table will also apply to the ghost table. Finally, at the right time, GHOST will rename the original table with the ghost table. All of the operation on the table is quite simple and can finish only in seconds. And they will run in parallel with other queries, so it's not increase the replication delay. As a cloud service provider, we must ensure that the MariaDB we provide to the customer should be a high availability service, which means that if the master node that currently provides service to customer has gone, the slave must replace the must in time to continue to provide database services for a replication. At this time of failure, the replication delay of the database must be small enough to avoid data loss. The most difficult problem we encountered was table without any index, because binary format is set to row by default. Every insert, update, delete operation will record as change of each row in the binary. For example, the table of order has 5 million rows in it, and we want to delete order where all the data before last month. This delete query will record 5,000 rows of data delete in the binary. So there are 5,000 queries will execute on the slave. If the table of order does not have any index like this, there will be 5,004 tables again on the table of order with 5 million rows, and you may get thousands of replication seconds, delay seconds. As a cloud service provider, we cannot force our customer to add index to the table, so we implement a hidden index, especially for such table to avoid replication delay. Firstly, when user create a new table, we will check whether the table has any index. If there are no index, we will create a new hidden column for the table and add an index of column as the red color text. The circle execution plan of full table scan will be changed. Secondly, when the user alters the table, it is necessary to check whether the modified table contains other index besides the hidden index. If the user adds an index, the new hidden index needs to be cleaned up. We will change the statement like this. And this is the final table definition. Additionally, in order to prevent users from accessing the hidden column and hidden index, we need to restrict the privilege of this column during select, insert, update, delete, and show operations. For end user, does not need to notice the existence of hidden column and hidden index. From the version of 10.3.3, MariaDB has provided a feature an invisible column. Here we create a table of items with an invisible column discount. The column cannot be accessed unless explicitly mentioned them by name. As you can see, the second insert will return error, and you will not get the column when you select star from items. But if you explicitly select the discount column from the table, you can get the value. We change the implement of this feature for hidden column. The biggest difference of hidden column from the invisible column is the privilege. User without backend privilege cannot read or access the hidden column. It will return error of unknown column, like this. Another similar feature is the invisible index introduced in the version of 8.0 of MySQL. Here we have a table of items. If you select the information from the table of items ordered by price, it can use index condition for range index scheme as circle execute plan. But if you change the index to invisible, the circle executing plan will change to full table scheme. So the invisible index of MySQL is not what we need for hidden index. The invisible index of MySQL is not visible to the optimizer, but our hidden index needs to be visible to optimize, which only hidden to the for-end user. At the end of this talk, let me summarize the main content of this topic. We start from the MySQL replication infrastructure and reviewed the problem caused by replication delay and how can we get the second of replication delay. Then we go through the parallel replication improvement introduced by the version of 10.0 and 10.1 of MariaDB. After that, we try to solve the problem of replication delay caused by long query like big, delete, and DDL. Finally, I introduce the hidden index solution implemented by WatchTag to help the non-index table. I hope that through my 30-minute introduction, you can understand MariaDB's effect to reduce replication latency and give you some advice for reducing the delay on the replication. Finally, thank you very much for participating in this discussion of topic. And thanks very much for MariaDB Foundation for organizing of this conference. If you have any other question, please send me email at pickup.watchtag.com. Thanks very much.